Hi guys, and welcome to Functioning Ecosystems Part 2. Now, if you've gone through Part 1, you should have a good understanding of some of that transfer of energy and a real, idea of the key definitions we're looking for within this unit. So let's get going into today's learning goals. So the learning goals for this lesson is to analyze and calculate energy transfer, so looking at food chains, webs, and pyramids, and transformations with ecosystems, including loss of energy through radiation, reflection, and absorption, efficiencies of energy transfer from one trophic level to another, and also biomass. So let's get going. This is a biggie, so strap yourself in. We're going to be here a little while. Now, calculating energy transfer and transformation. So the energy originating from the sun is used by organisms to perform work, whether obtained directly or indirectly from sunlight. We did learn that sunlight enters into the ecosystem. Photosynthetic organisms such as autotrophs or producers produce chemical energy in the form of glucose. And we can see that this carbon dioxide this carbon here has now been transferred to the glucose. That is then used for cellular respiration by plants and animals together. And as a result of cellular respiration, some of that CO2 is released back in. We also looked at the fact that we do have a bit of different levels of trophic levels here. So we've got our producers, we've got our then first order consumers, our herbivores, which eat plant material. We've got second order consumers, so those that eat, for example, the herbivores, and so on. All right, so third and potentially higher consumers. And that's the information you should have. So sunlight has come in. Now, solar energy can be lost through radiation, reflection, and absorption. Here you'll notice that we've got incoming solar radiation 100%. Some of that is reflected from the clouds. So some sunlight is reflected from the clouds, so not all actually will make it in. 20% of the radiation is absorbed by the atmosphere and clouds themselves. So again, we're losing some of that energy. Not all of it is getting in. So 50% of direct and diffuse radiation is then absorbed. So again, this word we're looking at that's important, absorbed by the land and sea. Some of that radiation that does get through is then also reflected from the land and sea, and 5% is backscattered to space by the atmosphere. So one of the key things here is not all energy or incoming radiation is actually made available to those plants. Some is lost via radiation, some is absorbed here, and some is reflected. And that's really that first key learning goal, that you can understand some is reflected, some is absorbed, and obviously not all is therefore made available to those photosynthetic organisms. When we consider food chains and food webs, they are basically qualitative and predictive models that allow ecologists to monitor energy flow within an ecosystem. When I say qualitative, here we're talking about kind of think literature, words. This is different to quantitative, which uses numbers or a numeric way. So let's look at the difference between food chains and food webs. Now, a food chain is a linear arrangement of organisms showing the flow of matter and energy from one organism to another through a feeding relationship. So when I mean linear, you can see that I go from my plant, my producer, to my primary consumer, to my secondary consumer, to third, and to quaternary consumer. And here I've got a terrestrial food chain. Here I've got an aquatic food chain, which starts with my producers, my phytoplankton, to the zooplankton, to herring, to tuna, and then eventually to killer whales as my quaternary consumers. Now that is a food chain. It's linear. It's going in one direction. This differs to a food web, which shows all of the possible feeding relationships between organisms in an ecosystem. And this will consist of many interlinked food chains. And this is a much better representation of the relationships that are occurring in an ecosystem, because you get all of that interconnectedness. You notice down here we've got 5 producers in this sort of desert scrub sort of ecosystem. We then have 4 primary consumers. Here we have then, and this guy here is also primary consumer, so is this. They also act as a secondary consumers because they're omnivores. All right, so then we've got these secondary order consumers. You've got your third order consumers, and then your quaternary consumer up here, which is consuming these ones. And again, it's consuming some from the second, and it's also consuming the snake from the third order. So you'll notice this food web really does enable you to see the relationships that are occurring in the ecosystem in a more detailed way than a food chain. So let's have a go at testing your understanding. Identify the producers in this marine food web, identify two omnivores, identify a food chain in which larger crabs function as a tertiary consumer, and determine the positions in the marine food web that a sea otter would occupy. So pause this video here now and give you a chance, and then I want you to flick over and we'll go through the answers. To begin, identify the producers in this marine food web. So the producers are those base organisms, those organisms that undergo photosynthesis. And when you look here at the base organism, you've got kelps and other algae and microscopic planktonic algae, which is the answer. Identify two omnivores in this ecosystem. So we're looking for those organisms which are consuming both plant material and other consumers. One that jumps out straight away. I can see the sea urchin eating this kelp, and I can see it eating sessile invertebrates. Sessile invertebrates themselves are one. I've got larger crabs, which I can see. I've even got drift algae and dead animals. They're eating producers and both other organisms. So you could have had any one of those four. Identify a food chain in which larger crabs function as a tertiary consumer. So a tertiary consumer is one that consumes secondary consumers, which obviously consume primary, which consume producers. Looking at one that stands out right away, just directly linear here. So we've got our microscopic planktonic algae, our planktonic invertebrates as primary, sessile invertebrates as secondary, larger crabs as tertiary. But there's a variety of other ways you could have gone. Okay, so if you can look through there, you'll find several others where the crab is that tertiary that you can put down. You can see some of the answers there. Determine the positions in the marine food web that the sea otter would occupy. Well, the sea otter is going to occupy several different ones. I can see here that it's a secondary consumer. I can see it's a tertiary. I could see if I go through this way, it's a quaternary or a top consumer. So it will, I guess, be in a variety of different positions depending on which food chain you actually follow in that food web. So you can see secondary, tertiary, quaternary, or a top order carnivore there. And even from then, they're even eaten by sharks, which are up here. So this is quite a large food chain. Doesn't often actually reach those levels that it is, in this case, in that food web. Looking at food webs again, construct a food web based on the following description of feeding relationships in an ecosystem. Then it says identify the trophic levels occupied by the kookaburras in this food web and predict the impact of removing Daphnia on the food web on both frogs and fish. Once again, pause the video. I'm going to go through these answers just so you can do it, but make sure you have a practice at doing it yourself beforehand. Flipping over right now. And when we start with our food web, we've got our producers, so we've got our wheat in the farm, our waterweed, and we've got our algae. Then you put in your primary consumers, so you should have had your mouse, your water beetle, and your Daphnia, are these funny looking little creatures over here. Going on to the second order consumers, we've got our snake, our frog, and our fish. And our tertiary consumer here, we've got the kookaburra. Now, the kookaburra is not only a tertiary consumer, as you can flow through, 1, 2, 3, 4 here. So it's eating the second order, which is eating the primary. It's also a quaternary consumer, because if I follow this one or this one, either way, okay, so you've got primary, secondary, tertiary, quaternary, all right? So it would have both of those. And the last one, what would happen to the frog and Daphnia's population if we were to, frog and I should say the fish, if we were to remove the Daphnia from this food web? Now for the frog, it at least has water beetles, so it would not be impacted. Given this food web, that the fact that the Daphnia is the only one that this fish currently is shown as eating, well, it would have quite large consequences on its population because its main food source will be lost from that ecosystem, and depending on what else is available, well, it might not survive, or at least the frog does have other options of food it can consume, okay? So hopefully all that makes sense and you're able to construct that food web. One of the key things I'll just highlight in this food web, because I didn't earlier, but I'm sure you picked it up, the arrow has to point in the direction that the energy is going. And you must do an arrow. You can't just do a line. I'll mark you down. You cannot do it the other way. I will mark you down, okay? You need to make sure that you are showing that arrow going in the direction that that energy will flow. And that's an important thing in both food chains and food webs. So the arrow always points in the direction that the energy is going to go. Looking at this, so we're going to start going into calculating these energy transfers now. So at each trophic level, a proportion of the available energy is either used to fuel the needs of the organism or lost as heat or waste material. And due to inefficiencies in this process, the remaining energy that is available to transfer to the next level is not as much as what was originally available. So we're going to look at that loss of energy. So the basic idea is organisms are going to lose energy via heat from metabolism and also as waste to the environment. Therefore, the amount of energy that's available at the top for tertiary consumers is nowhere near as much as was initially made, or our net primary productivity, by our producers. This is really showing your net, because obviously they have lost some energy too via respiration. Get into it. When we look at these energy transfers, there are a couple important things you have to understand. So producers will use sunlight to make their food. The amount of energy captured by photosynthesis we refer to as our gross primary productivity, which you should remember is GPP. When you consider this, so you've got the energy from the sun, not all of that energy from the sun is used. Some of it is reflected back and therefore not absorbed by the producers, and some of that energy is lost via metabolic processes, i.e. undergoing cellular respiration, and that energy is lost as heat to the environment. When that plant dies, some of that organic matter is lost as waste. So dead plant material is available to detritivores and decomposers, who once again will undergo cellular respiration and more of that energy is lost. What is actually available to the next trophic level we call the net primary productivity. So this is the biomass, i.e. energy, that's going to be available to the primary consumers, to the herbivores. So you have to understand that energy is lost via respiration and waste, and when you're considering producers, that some of that energy is actually reflected, so some of that light is reflected and therefore not used. So not all of that energy that's actually hitting the plant will be able to be used in photosynthesis. So there's two key terms we looked at here: net primary productivity, which is the amount of energy available to the next level once you take the gross primary productivity minus the energy that's going to be lost to respiration. Okay? When we consider consumers, so they're going to ingest food or consume food. So these consumers will eat food. This is the amount of energy gained. So consumers obtain their energy from various sources. So this could be plant tissue, animal tissue, dead matter, or detritus if you're a worm. So consumers rely on living organisms or particulate matter for their energy. Particulate if you're a worm, just to ensure that you understand, we're talking about detritus there, or for example scavengers like crabs and things like that. Okay, so consumers rely on these organisms which they've ingested. So consumers eat food. Then they are going to lose some of that energy as respiration. And most of that energy compared to waste is going to be lost as respiration. The greater amount of energy, as you can see represented by these arrows, is lost as respiration as a result of metabolism. They will also lose some energy in metabolic waste such as urine and feces. So not all of that food that they consume is going to therefore be used as energy that can be passed on to the next trophic level. So some is going to be lost as waste in urine and feces, and other is going to be lost as respiration, which is a larger amount. Then some of that energy will be available to be passed on, and we call this net production. See, the key thing missing here is that word primary, because these are not plants. So this is the net production, or the amount that's available to be passed on. When you consider how much they consume, well, we're talking about their gross production. All right, so the amount that's actually sort of consumed there. However, when we take out, just like we did with the plants, the energy loss is respiration, we have our net production. So this is the biomass, or the energy available to the next trophic level. For herbivores, this amount will be the net secondary production, because obviously they're the second ones in, and so on. But we'll tend to just refer to it as net production and not get too fancy with secondary and so on. So the amount of energy that's actually available to be passed on is about 10% from one trophic level that gets passed on to the next trophic level. So it's not efficient. We're losing 90% of that energy that was once ingested, for instance, by those animals. So about 90% is transformed by metabolism, which is basically fancy idea there for respiration, into heat energy and loss to the surroundings, or remains as chemical energy in both the uneaten portion of an organism and its body waste. So to get this little diagram down, we've got energy absorbed from previous trophic level is 100%. So they've taken that energy in, they've ingested it. So this is now what's available at this trophic level. You're going to lose approximately 80%. Now these numbers are not exact, okay? It's an approximation, a generalized amount. About 80% of that energy that's taken in, that's ingested, is going to be lost as metabolism or heat. About 80% of that is going to be lost as detritus, okay, so that organic waste material. So you've got different waste such as urine, but mostly feces, and the energy that's available to therefore be passed on for the next level to consume, the next trophic level, is about 10%. So you can see that we've got about 10% that's going to be passed on throughout the trophic levels. To visualize this, if we started off with the sun at 100 litres, well, the plants take in about 10% of that energy that's available to them. So you've got about 10 litres, first order consumer 1 litre, 100 mils, 10 mils. By the time you get to your fourth order or quaternary consumer, you've got about 1 mil of biomass or energy available. Now this is very generalized, and quite often these earlier trophic levels are more efficient, like producers do tend to be more efficient than these animals up here due to the extra amount of metabolic energy that's lost, particularly when we start talking about endotherms and stuff like that. However, we won't get too fancy at this stage. Just understand that as you move throughout the trophic levels, you are losing energy. Approximately 80% is lost as heat through respiration, about 10% as waste through urine and feces, and then about 10% gets passed on for these organisms to actually ingest. So energy loss is really what limits the number of trophic levels in the food chain, usually to 3 or 4, very rarely more than 6 lengths. Now, if we looked at that example we did earlier with the sea otter to the shark, well, we actually did have 6 lengths in that, but very rarely will you ever get more than those 6 lengths. I guess you could chuck in humans eating the sharks, but again, that's a different story altogether. So the closer a consumer's trophic level is to a producer, the more energy is available to be transferred. So you can see primary consumers obviously have more energy than the tertiary consumers. So you're looking at 1,000 joules of energy to 10 joules. So you get the idea. This is the perfect sort of 10% pass on here. This amount of joules obviously is very different there, but you can see that you're getting that 10% being passed on, and that is what limits the number of trophic levels to 3 or 4, because not all energy that is taken in or consumed by one trophic level is available to be passed on, because some is going to be lost as waste and some is going to be lost as metabolism and heat to the environment. So trophic efficiency is this term we use, which is the percentage of production transferred from one trophic level to the next. So when I look at the trophic efficiency here, I'm looking at 10%, because 10% of that energy is passed on. So that is the trophic efficiency, or sometimes we'll just say the energy transfer. So a lot of textbooks and sites will use trophic efficiency. I do see that this syllabus tends to talk about energy transfer, as you can see here, rather than trophic efficiency. So I'll use trophic efficiency and energy transfer sort of interchangeably here. So trophic efficiency, or the energy transfer, is the energy produced by an organism occupying a particular trophic level and is divided by the energy available from the previous trophic level. A key thing here, sunlight is not a trophic level, all right? Sunlight is not a living organism and is not a trophic level. So when you are calculating energy transfer or trophic efficiency, you are not actually calculating it from the producers. All right, so that is something completely different there. That's going to be looking at gross primary productivity. So please do not calculate energy transfer for those producers there. That is a different thing altogether, because for this formula, it's the obviously the energy that's produced by an organism occupying a particular trophic level divided by the energy available from the previous trophic level. And we get this formula here, and I want you to write this down. So trophic efficiency or energy transfer is the net productivity of the organism, so the amount of energy that's available after you subtract out the energy lost from metabolism and the energy lost as waste, divided by the net productivity of the previous trophic level multiplied by 100 to convert to a percentage. Might seem confusing to start with. Let's get into some examples to make this easy for you. So the trophic efficiency / energy transfer of the primary consumers in this diagram is going to be calculated using this formula. So we have our primary consumers. Now this is net productivity and this is gross productivity. Remember, we are looking at net productivity, and then we're looking at the net productivity of the previous trophic level. So to look at primary consumers, here I find the net productivity of them, and I'm going to divide it by the net productivity of the previous trophic level. So the one that's just there. Remember, I can't do that for the primary consumers because there is not a trophic level that exists here. So I will not be calculating primary producer transfer efficiency at all. So to put this into a formula, I have 1,103 divided by 7,618 multiplied by 100. So my trophic efficiency of my primary consumer, i.e. PC, in this diagram is 14%. I want you to now have a go at contrasting the trophic efficiency of primary consumers with the secondary and tertiary consumers. I'm going to give 3 marks for this question for you to fill in. So once again, pause the video, have a go yourself, see you can do it. I'll go through an answer. So if we start with our secondary consumers, I take my net productivity and I'm going to divide it by the previous level. So here for my secondary consumers, I have 111 divided by 1,103 times 100, which equals 10% for the secondary consumers. For the tertiary consumers, I take their net productivity, divide it by the previous level, which is 111. So I do 5 divided by 111 multiplied by 100, which gives me an efficiency of 5%. So now to contrast or to show the difference, so you're going to get 1 mark for getting this right, 1 mark for getting this right, and then 1 mark for actually doing your contrasting. So primary consumers had a trophic level transfer efficiency of 14%, which is higher than both the secondary consumers and tertiary consumers. This shows that primary consumer trophic efficiency is more efficient than secondary and tertiary consumers. And this is the key statement I'm looking for. If it's a data test and any type of thing, you're using your evidence and you need to make sure you're incorporating your evidence in. So I'm giving you a mark for using your evidence here. So for calculating both of them and using it, and 1 for your statement, which actually is comparing them. And as I mentioned, quite often the efficiency will actually decrease as you move down. Now that's not always, it does depend on the organisms there, but quite often it will decrease due to the nature of the organisms that are here. Here you often have your insects and that, which have very little energy loss to metabolism compared to your tertiary consumers, which are quite often endotherms, which lose a lot more energy to metabolism. So hopefully that makes a little sense why there might be a bit of a decrease. Now what this diagram does show, and hopefully you are getting it, is the fact that they are losing energy. This is as heat to the environment, which is larger than the amount of energy lost to the decomposers. So if I was given 2 energy loss values and I had to figure out which one was energy loss to metabolism, I'm always going the larger value there. And when you actually total these up, you should be able to notice that it is consistent here that the primary productivity is this added into this. Now this one isn't exact all the way through, but that is what you should be looking at, getting fairly similar. So now let's have a go. One more practice question. Calculate the trophic efficiency of the primary consumers. Looking at this, you know the formula, which is the productivity of the level that you're focusing on divided by the previous level multiplied by 100. So for this, you'll do 1,250 divided by 6,300 multiplied by 100 to calculate our trophic efficiency, and that's going to be 20%. And you can do that for the others as well. If you want to have a quick practice, you can do 250. So let's calculate for the secondary consumers. We've got 250 divided by 1,250 times 100, and we don't need a calculator for this because we're biologists, and we can clearly see that that is going to be 20%. And for our tertiary consumers, we'll do 50 divided by the previous level, which is 250 multiplied by 100, and that once again equals 20%. So they are as efficient as each other. Now one question I could do is I could say, well, calculate which energy which trophic level has the greatest trophic efficiency. Now remember, if I was to ask that, I would do my primary, I'd do my secondary, and I'd do my tertiary. I would not calculate my producers, okay? Because that obviously is not a trophic level, and our formula is the productivity of the trophic level divided by the previous trophic level. So I would calculate all those three, and in this case, I'd have to say they are all exactly the same. That should be able to get you to calculate those trophic efficiencies or the energy transfer between trophic levels. Very simple formula. Hopefully all of you can do that. Looking just to finish off, we'll talk about ecological pyramids. So ecological pyramids are a diagram representing the amount of energy, biomass, or they can also be a number of individuals at each trophic level. Basically, they show here your pyramid number, and it represents the amount. So as it gets thinner, you notice that it's getting a smaller amount. So this might be the amount of energy. The producers will have the highest. We know that tertiary consumers will have the lowest amount of energy. So there are three types of ecological pyramids that we looked at. So one represents numbers. This can sometimes be a bit messed up compared to the other ones. Notice here, numbers, very small for our producers. That could be because a tree actually is very few, but it takes up a large amount or produces a large amount of energy. Therefore, energy will look very different to numbers. So the number of trees might be small, but obviously it makes up a large biomass and amount of energy, where the numbers of flies is large, and then the numbers decrease as we move up the food chain. So that's one way they can be represented. They can also be a pyramid of biomass, and this is more our typical pyramid, where as we move up, the numbers are actually decreasing. And the same here for the pyramid of energy. There can sometimes be a few funny things, but we'll look at those examples as we go through. So a pyramid of numbers shows the number of individual organisms at each trophic level in the food chain. So if we look at here, this is another little weirdo where the amount of phytoplankton, its numbers are less than the amount of zooplankton. Then it kind of continues being a bit normal. One of the reasons is phytoplankton are produced so rapidly, but consumed so quickly by this zooplankton, that their numbers never actually become more than the zooplankton themselves. And that's a reason for this funny looking pyramid, which doesn't follow, I guess, a logical pyramid shape. Now, if the Egyptians started to build their pyramids like that, okay, we would have a bit of an issue. They wouldn't have stood up, but it still works and it is still a thing, okay? When you get these funny looking pyramids, you know that this must be looking at numbers, because it does and can occur like that. The same idea for biomass. It's a bit funny looking as well, because as I mentioned, these phytoplankton can reproduce so rapidly, but they get consumed so quickly by zooplankton, which does make it look a bit funny. So remember, biomass shows the amount of living matter, i.e. the mass of the organisms at each chain or each level of the chain. So you can see here our grass as the producers have the highest biomass, our primary consumers, rabbit, second highest, and fox has the least amount of biomass in that food chain. And then the pyramid of energy shows the amount of energy transferred through the food chain. This tends to have generally the same sort of trends where we increase up, simply because the producers obviously are producing the greatest amount of energy, and then we only get that 10% generally as an approximation transfer throughout these different trophic levels. That can differ. As we saw in that other example, we had efficiencies of 20%, so that can change, but the pyramid of energy will have a more normal shape. And to be honest, that phytoplankton, zooplankton is one of the cliche tricky ones when it comes to biomass. One of the only ones that will ever be represented like that, but numbers obviously can be represented a bit sort of inverted in a way, because those producers can often be quite large organisms and therefore very few numbers of them, particularly when dealing with trees. So explain why the pyramid of numbers can be inverted, but the pyramid of energy never can be. I've sort of explained that a little bit, but I want you to have a think, write down an answer for yourself, see how much you're actually listening, and I'll go through an answer. So once again, pause, and I'll go through an answer for you. So a pyramid of numbers can be inverted when a producer is a large organism, and therefore a small number of producers is capable of supporting a large number of herbivores. So if I have a certain amount of trees here, they might be very large, but I only need few of them to support many insects. Okay, in one tree, I could have hundreds of insects living. where a pyramid of energy can never be inverted because energy is always lost at each trophic level, either as energy from metabolism or as chemical energy in body waste or the uneaten portion of an organism. Because when the organism eats, they're not actually consuming all of the organism they eat in some cases. Sometimes they are, but most often an insect won't eat all of the plant. There's still leaves there. And an animal won't necessarily ingest all of the bones and everything that are there. So energy can never be inverted simply because there is energy loss at each trophic level as a result of things like metabolism and waste. Remember, metabolism is the greater amount of energy lost from that ecosystem or from that food chain there. Hopefully that has helped you with energy transfer, so you understand some of the ideas that some of that energy can be reflected, absorbed when dealing with plants, so that sunlight coming in, and you understand what food chains are, that simple linear diagram in food webs, which contain multiple links to that food chain. You can also calculate energy transfer or transfer efficiency by dividing the trophic level you're considering by the previous trophic level. Remember, you can't do that for producers. It's a common little error, something I want to make sure you clear up there. And we've also got things like ecological pyramids, which can represent numbers, energy, and biomass. Remembering numbers can be inverted, but energy never can be. That should have helped you with all of those things. As always, guys, if you need anything, let me know.